Hello friends, in this video, here in this video we will see the stress strain diagram for both ductile and brittle materials. So first we will discuss stress strain diagram for ductile materials. So generally ductile materials are those which are capable of having large strains before they are fractured. Ductile materials can withstand high stress and are also capable of absorbing large amount of energy before their failure. A ductile material has a large percentage of elongation before failure. So generally some examples of ductile materials are aluminum, mild steel and some of its alloys, that is copper, magnesium, brass, nickel, bronze and other. So now we'll see the stress strain diagram for ductile materials, especially for mild steel. So this is the stress strain diagram for ductile materials. So in this diagram we are going to observe the different stages. So from origin to up to this point is some straight line, and then it has some curve, and then it has some large curve. After that, at the end point it will fails. So generally first in stress strain diagram, on y-axis we will take stress, on x-axis we will take strain. So now we will see the different stages of stress strain curve of ductile materials. So actually this is the stress strain diagram for ductile materials. So now we are observing here different points P, E, Y1, Y2 and UTS, and last one is breaking point. So first we have to observe this point P. So this point P is called as proportional limit. So generally it is represented by sigma PL. Sigma PL means proportional limit stress. So here the proportional limit is the point on stress strain diagram which shows the highest stress, at which stress and strain are linearly proportional to each other, where the proportionality constant is E, known as modulus of elasticity. That means above this point stress is no longer linearly proportional to strain. On stress strain curve, proportional limit is shown by P. It is denoted by sigma PL. So it means that up to from this origin point to P, both stress and strains are increasing linearly. Okay friends. So generally for mild steel the limit of proportionality occurs at 230 megapascals. And next stage of stress strain diagram is point E, that is called as elastic limit. Yep. So here elastic limit is the point which shows the maximum stress that can be applied to the body without resulting in permanent deformation when stress is removed. At elastic limit, when the load is removed from the body, it returns to original size and shape. At elastic limit, stress is no longer linearly proportional to the strain. It is denoted by sigma EL. So at this point, the corresponding stress is elastic limit stress. For stress strain diagram of mild steel, elastic limit is just close to proportional limit. So this is very close to elastic limit. Okay friends, and then next stage of stress strain diagram is point Y1. Next stage of stress strain diagram is point y1. So what is this y1? What is this y1? So this y1 is called as yield point, and also here also we observed y2 is also another point. This is also a yielding point. So this y1 point is called as upper yield point. This y2 is called as lower yield point. So what is this yield point? Now we will see. Yield point is the point which shows the stress at which a little or no increase in stress results to large increase in strain. That is, material continues to deform without increase in load. At this point, the material will have permanent deformation. It is denoted by sigma y. For steel, yield point is also just above proportional limit. Yield point is of two types, so that is upper yield point and lower yield point. Upper yield point is shown by y1 and lower yield point is shown by y2 as in our diagram. Okay friends. Among the common materials, only steel exhibits yield point. For mild steel, upper yield point occurs at 260 megapascals and lower yield point occurs generally at 230 megapascals. Okay friends. And next stage of our stress strain diagram is UTS. UTS means ultimate tensile strength. Ultimate tensile strength. Generally it is represented by sigma U. That means corresponding developed stress is ultimate stress. So in this we will observe, as the stress on the material is increased further, the stress and the strain increases from yield point to a point called ultimate tensile strength, where stress applied is maximum. Thus, the ultimate tensile strength can be defined as the highest stress on the specimen which it can withstand. For mild steel, ultimate tensile strength occurs at 400 megapascals. It is denoted by sigma U. So generally it is the maximum stress. So where we will observe maximum stress in the stress strain diagram. So that is observed at UTS. And next, finally, the last stage of our stress strain diagram is F. So that is called as fracture point. So corresponding stress is called fracture stress. So this is now we'll see the fracture stress. So here, after ultimate tensile strength, the applied stress decreases until the stress is obtained where material fractures called fracture stress. Fracture stress is also called breaking stress. It is denoted by sigma F. Okay friends, now we will observe different regions under area of stress strain curve with different colors. So already based on the diagram we will observe the stages are elastic region stage and plastic region, yielding region, strain hardening region, and necking. So these are the different regions we observed from stress strain diagram. So and similarly, next we will discuss stress strain diagram for brittle materials. In the brittle materials, we are not observing different points. So just here we observe only. So here we observe only proportional limit and elastic limit. And last one, ultimate yield stress. Now, so this is the stress strain diagram for brittle materials. So from origin to up to this exact straight line, so this is called proportional limit. Some proportional limit to just increases, so that is just you observe some small curve. So this point is called elastic point, and this point is also called as ultimate tensile strength point. So that means at this point the material will break. So generally these properties are observed in glass. Glass is the best example for brittle materials. Glass is the best example for brittle materials. Okay. Okay, friends. Thank you. Next, we will discuss the properties of materials in the next class. Thank you. Thank you very much.